In this lesson, we're going to take a look at early models of the atom from the Greek philosophers up to Dalton. Now, in the video by Carl Sagan, he went through and described some of the things that Democritus had to go through. But one of the things I want you to take from that video was that he was a Greek philosopher. Not a whole lot's known about him because of how old or how long ago it was, and a lot of his writings and teachings have been lost over time. What is known is that he was greatly influenced by his teacher or mentor, Leucippus, and either he, together with Leucippus, or Democritus on his own, it's not necessarily known for sure, developed a mental model of the atom. And the reason why I say it's a mental model of the atom is because there actually weren't any experiments conducted, only reasoning. So the philosophers would look around and make observations of what they saw and try to reason as much as they could out of what their observations were to determine what was happening around them. Why were the things that they were seeing happening the way that they were seeing? And his model of the atom was pretty simple. Everything could not be cut any further down than the atoms that made them up. Without going into a lot of detail, they had different shapes and structures to help hold them together. That's how we have our matter. But in the end, we'll just stick with a simple model that everything was made up of what was called atomos, which are particles that cannot be cut. It wasn't for another almost 2,000 years before we got to a cohesive model of the atom based on some experiments. Leading up to that was what many consider to be the father of modern chemistry, Lavoisier. He was a French nobleman during the late 1700s, and he did many, many experiments. He was very diligent about his experiments, and he tried to make the science of chemistry as quantitative as he possibly could, taking measurements as accurately as he possibly could. He was not the person who discovered oxygen and hydrogen, but he gave them their name. At this time in history of science, there were many different things happening, many different people doing experiments. Most of the time, on their own. It wasn't centrally located in a school. And Lavoisier was one of those. He was a fairly well-off, affluent person, and these are the people at the time who had the time and the money to do their own thing. They would go through and do their experiments. If something interested them, they'd go out and pursue that. And Lavoisier was interested in chemistry and making the measurements as well as he possibly could. The balances that he made are just as good as the best balances that we use in our chemistry classroom here at Center Grove. And this is back in the late 1700s. They were all mechanical, not electronic like ours. One of the most important things that he determined was that when studying chemical reactions and measuring the masses of the elements and compounds that were involved in these chemical reactions, he found that mass did not change from the beginning of the reaction to the end. So if you were to measure out all of the reactants as accurately as you could possibly do so, and make sure that during the reaction you contained all of that matter so that nothing was lost or escaped from the reaction, and you measured that matter afterwards, you would find that you have the exact same mass as what you began with. We now know this as the law of conservation of mass, and this was a huge step forward in helping us to get to a closer or better understanding of what we now know as chemistry. The next scientist that came about, or not came about, but in the stepwise progression towards a cohesive model of the atom, is Joseph Proust. Now, the dates I have here are not for his birth and death. These are the time frame for the experiments and discovery that he presented. In 1794, he published a paper showing that compounds have specific set ratios. To us, this seems pretty logical. I mean, even as introductory chemistry students, you have seen chemical symbols and formulas. We've seen several labs where you've gone through and determined or looked up the formulas for some compounds. And we accept now the fact that a compound's formula is what it is. But up until this point in time, it wasn't known that those were set. Now, the experiments he carried out, he used several different compounds, but they tried to keep them as simple as possible. And one compound that he used was copper carbonate. And that compound's made up of copper, a carbon, and 3 oxygens. And he would synthesize this compound in the lab, starting off with just copper and carbon and oxygen, combine them, do a chemical reaction to create that compound, copper carbonate, in the lab. Now, copper carbonate is not an uncommon compound found in nature. So what he would do is he would find copper carbonate in nature as an ore or as part of a mineral, isolate that, and then compare that to the copper carbonate he'd found in the lab or made in the lab. And no matter what, he found that the proportions of the elements in those compounds were always the same. He did the same thing with other elements, 2 other elements, tin and iron. He would take and measure or make different oxides of tin. There are 2 different oxides of tin. One would be called tin 2 oxide, and its formula would be SNO. And another oxide of tin is tin 4 oxide, and its formula is SNO2. He would make these compounds, and no matter what he did, they always came out with the same proportions, and they always came out with different properties. So tin 2 oxide is different from tin 4 oxide. They have different proportions. We now know this as law of definite proportions. Sometimes it's called definite composition. If you were to dig up a chunk of tin 2 oxide in Europe, it's going to have the exact same formula as tin 2 oxide here in the United States. If you go to Jupiter or Saturn, you go to the moon, if you were to find tin 2 oxide, it's going to have that exact same formula. One of the things that we look for in our explorations of space is we look for water. Water has the same formula no matter what. If you find that you have water, you know that the formula is H2O. And these lead us to John Dalton. John Dalton is the first scientist to develop a model of the atom that is based on experiment. Now remember, we had the Greek philosophers, back in 320 BC, so we're looking at over 2,000 years before Dalton, coming up with a model of the atom simply based on observation and what they looked and saw around them. But John Dalton's model of the atom is based on experimental evidence. He built on what Lavoisier's law of conservation of mass was. He built on Proust's law of definite proportions. And John Dalton also carried out experiments. He would use other people's information, other research that was done, and incorporate that into his ideas. He also then assumed that the elements combine in simple ratios by mass. So we know that this is building upon Proust's law of definite composition or definite proportions. What he's assuming here is that the atoms themselves are combining in simple ratios because you can't split these atoms. And probably the most important part of his law came the law of multiple proportions. And this law is, again, kind of like Proust's law. To us, it makes sense. We know this. But again, at the time, this is groundbreaking. And what Dalton's experiments uncovered was that you could make different compounds using the same elements. For example, we know water is H2O, but I'm also sure that many of you have hydrogen peroxide in your medicine cabinet at home, and the formula for that compound is H2O2. Different compounds, completely different compounds with different properties, but they're made of the same two elements. Or the law of multiple proportions states that if two elements form more than one compound between them, the ratios of the masses of the second element, which combine with the fixed mass of the first element, will be ratios of small whole numbers. Let's take a closer look at this. Here's an example of the law of multiple proportions using compounds of nitrogen and oxygen. Quick explanation of a couple of things here. First off, these ratios. The ratio of masses is being used by comparing the mass of the nitrogen in N4 or NO4 to the mass of oxygen in NO2. So for the NO4, what's happening here is we're looking at a ratio of about 64 for the mass of oxygen compared to 14 for the mass of nitrogen. And we're taking 64 divided by 14, and we're finding that oxygen's ratio by mass in that compound is 4.57. For the NO2, we are looking at a mass of 32 for the oxygen compared to a mass of 14 for the nitrogen. And when we divide that out, we're going to get 32 divided by 14, which is equal to 2.28. We then go to the ratio. In the two different compounds, what we can see here is that the mass of the mass of oxygen in NO4 is twice the mass of oxygen in NO2. So the ratio is 2 to 1. The same is occurring with these other compounds as well. We've got a 4.57 ratio to 1.14. Now notice that the 4.57 here is the same because both of these compounds have the same formula. They have a 4 oxygens to 1 nitrogen ratio. Hence the 4.57 is the same in the first two of these. Okay? But in the second compound, we have only 1 oxygen atom compared to the 1 nitrogen atom. And in this case, we get a 4 to 1 ratio based on those masses. Again, you'll see that we have another 4.57, only this time around compared to a ratio of 0.571. Now, we'll look at these two compounds, and we'll see here that we have, in this case, twice as much nitrogen in the second compound and 1/4 the amount of oxygen in the same compound. So where we had a 4 to 1 ratio oxygen to nitrogen, we now have 1 oxygen to 2 nitrogen ratio. So it's going to make it look like there's 8 times as much oxygen in the NO4 than it is in the N2O. And you see the same things being done for the other compounds as we go along. Here's the key, and this is where Dalton's law of multiple proportions is coming in. All of these ratios are simple whole number ratios, which leads us to understand that you can have the same elements with different proportions making different compounds. In 1808, Dalton published what many consider to be one of the first chemistry textbooks that was after a while, was widely accepted. It took about 3 to 4 years before the information that he had presented spread out widely. Many scientists still did not accept his ideas that atoms are or elements are made up of atoms. But these are the 5 basic principles, and I'll make a comment about each one of them as we go here. His first statement is that elements are made up of extremely small particles called atoms. This is just a continuation of this idea from the 300 BCs, that we have these particles that are so small you can't see them, and that they are indivisible. The second statement, atoms of a given element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. Now, this principle is not necessarily true now. At the time, what Dalton knew was enough to be able to say this. But with better instrumentation, we understand now that not all atoms of the same element are identical in size. They're not all identical in mass. Their properties, though, are going to be identical chemically. When we start talking about the nucleus itself and the properties that the nucleus has, that's where we're going to get some differences in the properties. But for the most part, you cannot distinguish during a chemical reaction the different atoms of carbon that are called isotopes that we'll talk about later. They all act alike. And this is why, one of the reasons why, during their experiments, they were not able to identify any differences. And thus they assumed that all atoms of the same element are identical. The third one, atoms cannot be subdivided, created, or destroyed. Now, part of this, the created or destroyed part, is is a restatement of Lavoisier's law of conservation of mass. All of our matter, all of our mass is coming from atoms. And if they can't be created nor destroyed, then we have our conservation of mass. They can be rearranged. The subdivided part of the statement, though, is not correct. Now again, Dalton doesn't know about smaller particles. He doesn't know about electrons. He doesn't know about protons. He doesn't know about neutrons. He doesn't know about quarks. So this is why he says they can't be subdivided. So part of the statement's not true. I mean, we have a better understanding now. But the second part, with the created and destroyed, that is basically, again, an accepted statement for us when we are talking about regular chemical reactions. One thing that I want you to understand is that mass or matter can be created and destroyed, but that's only during nuclear reactions, and a topic that we'll talk about later on in this unit. The fourth statement, atoms of different elements combine in simple whole number ratios to form chemical compounds. It's not a definite restatement of the law of definite and multiple proportions, but kind of combines the two. The heart of what we're talking about in those two laws is here, that elements combine, the atoms combine, they form compounds. Those compounds are going to have definite formulas. Again, we talked about water being H2O always, but we also can make hydrogen peroxide. That's where the law of multiple proportions comes in. You can have different compounds from the same elements as long as they have different ratios. The last statement, in chemical reactions, atoms are combined, separated, or rearranged. That's what Lavoisier was showing, again in his law of conservation of mass and the experiments that he did. During a chemical reaction, you start off with one type of material, one type of atoms, one type of element, one type of compound, and you mix it with another element or another compound, and you get completely new compounds in the end. And it's those new compounds, they're still made up of the same atoms that made the reactants, but they're simply rearranged in a different pattern to give you the different compounds as a result of that reaction. And that's it for the earliest atomic theories. Our next topic, we will discuss the discoveries of the different parts of the atom and how we got to the point where we have a better understanding of the fact that we have a nucleus and electrons not rotating but existing around that nucleus.